So one day my teacher was going to introduce Lagrangians in physics class, and I've always wanted to learn it since I heard about it in PBS Spacetime. She was talking about the lampshade problem, which is quite a classic, pun intended, and everything was making sense, and she was proceeding with this integral and calculus of variations, and suddenly, Kosh? Apparently everyone was confused about why hyperbolic cosine appeared out of nowhere. Like, I don't see a hyperbola here. Now, being the nerd that I am, I've already been acquainted with this function that will proceed to be my arch nemesis for quite a good while, because I just seemed to miss the intuition for it that allowed me to work with regular trigonometry happily. I've seen hyperbolic trigonometry in engineering videos about catenaries and minimizing surfaces. I've seen it in Ike and Chris's videos about spinors and Lorentz boosts. I'm also not afraid to admit how good I felt about myself when I recognized the formula for adding relative velocities to be identical to the sum of angles for a hyperbolic tangent in my special relativity class. It's one of those topics that you know is important and useful, but I just never feel like I could understand it enough. Therefore, with all of my past confusion and questions in mind, I present to you stuff I wish I knew earlier about hyperbolic trig. Now, I started planning for this video in June and ended up diving into a much deeper rabbit hole than I ever expected. Well, it was kind of expected because it's math, but still. So, I hope you enjoy and have as much fun out of this potential video series as I did researching this topic. Let's start with basic definitions. I mean, how hard could it be? It's just trigonometry with an extra prefix, right? Well, sort of. Here's a list of different ways that trigonometry is defined. You have your two pre-calc definitions of trig, one within a right triangle with hypotenuse length 1, the other being the projection of the radius onto the x and y axes as the angle increases from 0 to 2 pi, or you can also see it as a point revolving around the unit circle. As you progress further in calculus or an ODE class, you may also recognize trig functions as the class of functions whose second derivatives look exactly like the original function, except that it has an extra negative constant. If you see this form, you immediately know that the original function is sinusoidal, or some linear composition of the sine and cosine function. Somewhere along the way, you may pick up Euler's equation or formula, which is known as one of the most elegant equations in math, and you begin to have some sense of how trigonometry is vaguely connected to exponentials. If any of these definitions sound unfamiliar to you, I'll try to include visuals as we go on, and also link to some videos in the description that help me understand them. Before we proceed, this video will assume that you understand basic concepts in calculus and some linear algebra, around the depth of 3Blue1Brown's Essence playlists. Some experience with differential equations and more abstract topics in math may be helpful, but not necessary. Starting from these four definitions, we can take a look at hyperbolic trig. Now, usually when this is presented to the students, you see this definition of hypertrig. Immediately you associate hyperbolic trig as closer of a relative to exponentials than regular trig, which is not untrue, but also the reason why it confused me at first because of the naming. Hyperbolic sine and cosine are the odd and even parts of e to the x. Turns out you can do this to every function with the following formula. If you are a physics or engineering student, you may also know that hyperbolic trig is the class of functions that satisfy this differential equation, which looks extremely similar to the one for regular trig. They also have similar patterns when it comes to derivatives and inverses. So from this, 3 of the parallels are already seen or vaguely hinted at, yet it leaves us with more questions than insight. For example, in trigonometry, it's defined with a right triangle. What is the equivalent geometric shape used in hyperbolic geometry? We can also notice that even in the wavy function definition of trigonometry, sine and cosine have a phase difference of pi over 2. Is there an analogous form of orthogonality or right angleness in hyperbolic trig? And what does it tell us about hyperbolic space in general? We can also see a very obvious periodicity in sine and cosine functions and how they're essentially congruent and can transform between them by adjusting the phase. How do these aspects manifest in hyperbolic trig, and how does it connect to the transformations between hyperbolic trig and regular trig just by adding imaginary numbers? So in this series of videos I'll publish in the future, hopefully I'll pull through with it, I'll attempt to answer these questions and introduce hyperbolic trigonometric functions with the relevant physics to contextualize it. The next episode will be on hyperbolic geometry, and I'll slowly build up to rotation matrices in special relativity, a tiny bit of group theory, and hopefully leading up to split complex numbers and drawing connections with regular complex numbers. I'm doing research as I go along, so feel free to drop comments or questions you find interesting.